Hello, welcome to Psych 2111. I am your instructor, Dr. Go Freddy, and I'm super excited to be teaching you this course and this content because we should ask ourselves, well, why? Why are you here? Why do you need to learn statistics in the first place? And yes, the obvious answer is because it's a required course, but it goes a lot deeper than that, and it's a required course for a good reason. And the good reason is this, okay? So you are going to go on after this class and you are going to learn a lot more about psychology, and eventually you're going to get into a career likely in psychology, right? Some of you want to be counselors or therapists or forensic psychologists or sports psychologists or you name it. Lots of different kinds of careers that you can move forward in from this major. The thing that all of those career paths have in common is this: they have found a way to operate at their current peak level, right? And so what do I mean by that? Well, let's take therapists, for example, right? Therapy has undergone a lot of shifts and changes over the years. There's now many different kinds of therapies, and some of them are maybe better for certain types of diagnosed disorders than others, right? And so the question you could ask yourself would be something like, well, if I want to be a therapist, I want to learn more about, let's just take a random one, generalized anxiety disorder. I want to know what is the best treatment for generalized anxiety disorder. Well, how would I know what the best kind of therapy is for somebody who has that diagnosis? Well, the reason I would know, the way that we would know, is through through research studies that have compared different kinds of therapies, probably both medication, drug related, as well as therapy and counseling related. And they've compared a lot of those different things and actually shown, well, what are the best kinds of treatments, the best kinds of ways we can help somebody with that diagnosis. And so the way you need to do that, though, the way you need to conduct research is with statistics. And the statistical methods that we use in this class are exactly the same types of statistical methods you would find in such a research paper that is actually trying to look into those kinds of things. So it's important that we know something about statistics so that we can then take it into the fields that we want to go in and be assured that we are doing the current best gold standard of whatever treatment or whatever focus that you end up in. And I am here to guide you through this class. Uh, I'm really excited. So without further ado, let's dive in. First of all, let's talk about learning objectives for the chapter. We're going to learn why we use statistics to analyze data. We'll learn about differences between descriptive and inferential statistics. We'll learn why there are so many different kinds of statistical tests, various methods we use to actually collect data, as well as how those methods will affect the type of statistics and statistical analyses we use. First up, let's learn why we use statistics to analyze data. At its core, statistics is really a tool. You're going to have these large data sets to work with. Sometimes there'll be hundreds of people who participated in a survey, who you collected data on dozens of different variables like IQ or blood pressure or whether they take their medications on time or bravery or happiness or just all kinds of different things that we might be interested in psychology. But you have to distill all that stuff down to make it usable and easy to interpret for other people and for yourself if you're a researcher, right? Knowing statistics also really helps you to understand arguments and make arguments based on statistics. You know, this includes things like worldwide surveys and polls, political polls, those kinds of things. You can also learn how to use statistics to solve problems in society or maybe in your careers. One kind of easy example of that is how satisfied customers are with your products. Let's say if you go into industrial organizational psychology. So a company like Target or something might send out surveys to their customers that asks, how satisfied are you as a customer here? Might have a 1 to 5 scale, 1 being very dissatisfied to 5 very satisfied. And we want to know, as statisticians, what can we do with this information? And it turns out that you can do a lot with just that single question, with a scale of 1 to 5, right? We could summarize the data. So we could say, well, on average, how satisfied are all of the customers? We can create an average score of all of their individual ratings. We could look at how varied the scores are. If you want to know, well, are most people, scoring in the upper ranges, so they are very satisfied, or maybe there's just a huge range of responses. Some people are not very satisfied, some people are very satisfied. That could be interesting. We could display average scores in graphs to help kind of interpret those. We could test predictions about whether our group of participants or customers is more or less satisfied than other groups of customers, maybe at different times or in different storefronts, like different locations of the stores. So there's all kinds of stuff we can learn with statistics. Oftentimes you can find statistics in media. So if you're looking at something like a political poll, it's going to say, X amount of people voted Republican, X amount of people voted Independent, X amount of people voted Democrat, et cetera, et cetera. Here we can actually see a stat that might be interesting to you, hopefully, which is that 87% of CU graduates become employed within 6 months of graduation. But sometimes news outlets will report statistics either inaccurately or not give the full story. So here's an example of like, well, if a news outlet displayed the information that, oh, people who regularly use cell phones more than 6 hours a day have higher rates of brain cancer compared to people who use their cell phones less. Well, we would definitely want to know, like, should I stop using my cell phone? Like that seems bad, but you have to know more details about the study before you can make any kind of conclusions. For example, you'd want to know how large was the increase in cancer rate? Are we talking about 30%? Are we talking about 0.0001%? You'd want to know more things about how the study was conducted, whether it was rigorous, whether it was blinded, whether they used experimental control. You'd want to know whether there's other differences in general, just like people who don't use their cell phones a lot might be a substantially different group of people that normally are healthier or something like that versus people who use their cell phones all the time or maybe less healthy and in general, and those are what is actually contributing to the cancer rates, right? And then finally, you'd want to know if the difference between the groups in terms of cancer rate is statistically significant. So not just that they are different, but that they're statistically significantly different. And we'll talk more about that when we talk about things like hypothesis testing and p-values. But basically, in order to know whether a 2% increase in cancer is different than like a 0.001% increase in cancer, although those numbers seem kind of different, you're not sure if they're actually different or not. Next up, we're going to talk about understanding differences between descriptive and inferential statistics. First up is descriptive statistics, and this is, as the name implies, just a type of statistics that is used to summarize or describe data. So again, you've got these big data sets with hundreds of people in them, dozens of different variables. Maybe you're looking at age, you're looking at ethnicity, you're looking at socioeconomic status, but you're also looking at things like IQ and extroversion and different personality variables, happiness and depression and anxiety. You want to maybe talk about the averages, so in other words, the mean depression scores, mean IQ of the sample, mean age of the sample. You want to talk about frequencies, which we'll get to in a second. You might also talk about variability, which is also called spread or dispersion of scores. So again, are a lot of the scores really tight and close to the mean, or are they really spread far, far, far apart? So if you have a scale of 1 to 7, again, are most of the numbers kind of around like 4 or 5, or are they just all over the place? Ages too, right? If you have not with a college sample, the ages are probably going to be like 18 to 21. But if you've got an adult population sample outside of the college, maybe you've got ages that range from 18 to 74, right? So you could also look at the distribution of those as well. Descriptive statistics are really nice because they help readers and viewers get an idea of what you're talking about, and you can put these types of descriptive statistics very easily into graphs. Like in this example, we've got people who came in and were either tasked with driving in a driving simulator, just paying attention to the road and what's in front of them. That's called the single task condition, versus the dual task condition was they were asked to actually be like texting on a phone or paying attention to a phone while they were driving in the driving simulator. And you can see in the top portion of this graph, the driving condition is related to mean response time to brake lights, meaning in the simulator, a car in front of them would put on their brakes, and so the brake lights would come on. And how long does it take before the drivers in these two different conditions would actually put on their brakes? In the bottom set of this graph, you can see that the number of crashes is on the y-axis, and the two different driving conditions are on the x-axis. So you've got, again, single task people. Well, there's only one crash from that group of people, versus in the dual task condition, who are paying attention to their cell phones, 6 crashes. So this first graph, you're looking at the average response time, that's RT is response time. And in bar graphs, you look at basically the top of the bar, right? So the mean response time of the single task group looks about 900 milliseconds, something like that. Whereas the mean response time of the dual task, meaning people who are on their cell phones, is above 1000, maybe it's close to 1100 milliseconds, meaning it took them longer to press the brake after they saw a car in front of them put on the brakes. And the bottom graph isn't about the averages, it's not average crashes, it's just a total number of crashes. So what is the actual frequency of crashes? In the single task group, one person got into a car accident. In the dual task group, 6 people got into a car accident. You might be interested in more than just the average response time for different groups of drivers. You might be interested in the variability. So like, well, did most people take a lot longer to respond to the brake lights in front of them, or were they pretty quick but with some outliers? What does the actual distribution of scores look like for all these different individuals? And so this might be, I just made this data up, but this might be response time for the distracted drivers, those in the dual task condition with their cell phones. And the mean was something like around 1100 milliseconds, which you can see denoted by this red line up and down here. But these bars are telling you how many people, which is the frequency, how many people in this condition got which response time. So you can look at this first response time, 900 milliseconds. Looks like one person spent 900 milliseconds before they were able to actually apply the brake. Then there's 2 people who took about 1000 milliseconds to respond, and 4 people who took 1100 milliseconds to respond, right? So you can see how far dispersed these bars are is a measure of variability or dispersion or spread. All those things mean the same thing in any given distribution of data, which is just a set of numbers for a particular variable. So descriptive statistics is able to tell us things like the frequency and the average, or the dispersion of different kinds of data, but you might also want to ask yourself, like, well, are these things significantly different? Like, is this average response time between the two groups, is that significant? Is it meaningful? And you can't get that with descriptive statistics. You'd have to go to inferential statistics, which we'll talk about next. Other than descriptive statistics, inferential statistics, like the name implies, an inference is a conclusion based on data, right? So inferential statistics are statistics that help you make some kind of conclusion or test some kind of hypothesis. So in the previous example, we're asking, does driving while texting result in worse driving performance than driving with no distractions. So those are two different groups. And we saw that the means were different in terms of response time and the frequencies were different in terms of how many crashes they had. But we don't know if those differences are meaningful or significant statistically. So in order to actually test that, we would have to use inferential statistics, like a t-test, which we'll talk about very soon, or an ANOVA f-value, or we could correlate those things. Well, you wouldn't use that here, but t-test probably. And so we'll talk more about that in future chapters. Another important idea in statistics is the difference between a population and a sample. So a population is the entire set of a particular group of people, okay? Whereas a sample is just a small subset that you take out of that population, and the sample are all of the people who are in your actual study, your experiment. It's not likely that, let's say, if you're a clinical psychologist and you're really interested in studying anxiety in adults, well, the population would be all adults with anxiety, right? Maybe even you want to say all adults with anxiety in the United States. That's a huge number of people, and there's no way to get all of those people into your study, right? Into your lab. So you take a subset of that population and you might invite maybe 100 or 200 or 300 adults with anxiety into your study. And that 100 or 200 or 300 people, that is your sample. And when we talk about populations and samples, we also have to talk about parameters and statistics. Okay, so a parameter is a number that represents some quantity or quality of a population. So, for example, if we were able to get an entire population's worth of data, so let's say all CU students, for example, could be a population. I want to know what's the average number of beers that all CU students drink in a week. If I was able to actually measure every single CU student and ask them, hey, how many beers do you have on average on a week? If I was able to do that, then that would be a parameter because we actually know something about the population. But if I more likely was only able to get a subset of CU students, let's say all of CU psychology majors, okay, and I asked them, hey, how many beers do you have in a week? Well, if I get that average, then that's going to be called a statistic. And this is kind of like, well, why do we have to know this? It's important because populations are what scientists want to know about. But we have to infer information about populations using samples. And so we have to rely on statistics, which come from samples. Now, an easy way to kind of remember if you need to use a parameter or a statistic, or if it's going to be called a parameter or a statistics, parameter and population both start with P, statistic and sample both start with S. So that's just a healthy or a helpful little mnemonic there. And again, parameters can be things like percentages or averages or standard deviations or something like that. The same thing is true for statistics. It just depends on if you're talking about an entire population or just a sample. And so the entire purpose of statistics and therefore of this class is that we're trying to understand something about populations, but we're doing that using data from samples because we can't take an entire population, a whole census of a population, generally speaking, that's very, very difficult to do. And so instead we can only take a subset of that population, which is the sample. We analyze the data, we look at different variables and how they relate to each other, and we try to make predictions based on what we're seeing or see if two or more groups are different from each other in terms of some variable. But we can only do that with a sample, and then we want to use that information to try and understand a little bit more about the population that sample comes from. Ultimately, statisticians and psychologists and scientists at large are interested in populations, but we have to use data from samples to infer something about those populations. All right, why are there so many different kinds of statistical tests? There's t-tests, there's ANOVA, there's two-way ANOVA, there's within subjects ANOVA, there's paired t-tests, independent samples t-tests, one sample t-test, there's regression, there's correlation, there's all kinds of different tests. Why is that the case? Well, first of all, we might want to look at the different processes of research. So for instance, in step one, we choose a research question. And in step three, we develop a hypothesis based on previous literature. But step four is how we actually design the study. And how we design a study around different variables that we're interested in looking at is going to determine which type of statistical analyses we use in step six. For example, we might come up with a research question: how does anxiety in college students relate to their scores on their final exams? Well, when thinking about how to design a research project around that question, we could approach it in a lot of different ways. And how we design that study is really going to change the type of statistical tests or analyses we should conduct. And we'll see in the next few slides a few different kinds of research designs or research approaches. So the last two learning objectives for this chapter are to explore different methods used in data collection and understanding how those methods affect the statistics used. The main two categories of research designs or research methods include experimental studies and correlational studies. And these are very different from each other, most notably in their ability to determine causality. Let's talk about what that means, but first we have to talk a little bit about variables. Variables are just different attributes that can vary across individuals. So this could be anything like age, gender, blood pressure, anxiety, happiness, test performance, you name it. Anything you can measure is a variable. And different types of research are going to use different kinds of variables. As kind of a silly example of this, I want you to tell me, did you have breakfast this morning? Now, this is a variable, right? Because some people eat breakfast in the morning, some people don't eat breakfast in the morning. So that's a between persons kind of variability. But there's also within person variability. Some days you might have breakfast and other days you might not, right? In experimental studies, we manipulate what's called an independent variable, the thing that we're actually changing, in different conditions. So if we use that example of student anxiety and affecting performance on final exams, we might separate students into two different groups and do something called an experimental manipulation, do something that's different to those groups. So in one group, we might try to actually engender anxiety, like we might actually try to cause anxiety in those students before a final exam. And in the other condition, we might either do nothing to them, so they'd be a control condition, or we might actually try to reduce their anxiety in some way. And then we would measure after the exam their grade on that final exam, which is our dependent variable. That's the thing that we're interested in as an outcome. Because in experimental studies, we're trying to establish causality. So the independent variable, x, actually affects or influences the outcome variable or dependent variable, y. So in this case, it would be we think that anxiety in students will affect their final grade scores, right? So anxiety in students is basically the independent variable, at least in the two different conditions that we might assign them to, and that affects the outcome variable, which is their grade, right? In experimental studies, we want to control for as many possible what we call confounding variables that might also influence the dependent variable, that might actually be causing the difference that we see in the outcome, which is the final grade, right? So it could be things like the temperature of the room. It could be something like the general health of students. If somebody has a headache, they're probably not going to do as well in the study. It could be how well they like the teacher. It could be how effective the teacher was. Like all these other things we would want to somehow control for because we want to increase what we call our causal inference. If we hold all these other potential explanatory variables constant, meaning we control for those things, the only thing that could affect the outcome, which is final grades, is what we change. And what we're changing in that example is whether we're giving students anxiety or not. So we know that the anxiety is what causes differences in those final grades. Now, in order to be considered a true experiment, you have to have random assignment. This random assignment is something that also controls for a lot of potential confounding variables, right? Because if you randomly assign people to those two different conditions, to be given some kind of intervention that actually increases their anxiety, which is not very ethical, or in the other condition to decrease their anxiety, right? Well, a potential confounding factor is some of those students naturally will come into the room with more anxiety than other ones, right? And so you have to randomly assign students to these two different conditions so that those differences in just natural differences, natural variation in anxiety between students cancel each other out between the two groups. So you know without a doubt that it's like, okay, well, I have in group A, some students will have some anxiety, some students will have low anxiety, some students will be neutral. And in group B, some students will have high anxiety, some students will have low, some will be neutral. Now, when I do my experimental manipulation, it should affect one group more than the other. And that's how we know it actually does cause an effect on the outcome variable. A different type of experimental setup is what's called a quasi-experimental design. This is where you have two groups that are already sort of naturally formed, and you can't, for whatever reason, randomly assign them. So, for example, you might compare final grades from students who already have self-reported high anxiety versus students who self-report that they have low anxiety, but you didn't actually randomly assign them to those. That's just what they kind of, walked in the room with. Another example of that is like if you're trying to look at blood pressure in people who are pregnant versus people who are not pregnant, you can't randomly assign people to become pregnant, right? Like that's not how research works. That would not be a good experiment or study. So you have to just find people who already are pregnant and find people who are already not pregnant and then compare them. That would be a quasi-experimental design. Besides experimental studies, there are also correlational studies, and these are designed to examine relationships between different measures of behavior or different cognitive functions or whatever, right? These are about natural relationships between variables. There's no experiment, meaning nobody's randomly assigned to anything, and there is no experimental manipulation. It's just, you know, take a bunch of people into a room and have them answer survey questions or whatever. And you're just trying to see if some of the variables are somehow related to each other in some way. So you might be interested in, I don't know, like, does the amount of sleep that students are getting impact their overall GPA? So you would just ask them, hey, like on average, how many hours of sleep do you get per week? And then you would want to see if that is just related to their overall GPA, right? And probably there is some type of positive correlation between those two things, which we'll talk about in a second. This doesn't tell you, though, about actual causality. It could be the fact that, the amount of sleep you get directly influences your GPA, or it could be that, other things affect both your sleep and your GPA. So you can't really be sure. You also don't know if, like, which direction does it affect people? Is it that low GPAs cause people to freak out so they get less sleep? Or is it that lack of sleep, low sleep, causes lower GPAs? You wouldn't actually know based on correlational studies. kind of a silly, famous example of this is that there is a positive correlation between ice cream sales and homicide. And so one potential interpretation would be, does that mean that people who eat more ice cream are more likely to commit murder? Like, obviously, that's not what actually is happening. There's a hidden third variable here, which is heat, right? And so, as it gets to the summer months, people get hot outside and they both want to cool down and also get more aggressive. Heat causes aggression. There's been studies that show that. And so this third variable that's kind of invisible if you didn't measure it is actually causing both increased ice cream sales and increased homicides at the same time. But you could mistakenly make the conclusion that increasing ice cream sales causes increases in homicide. And like I mentioned previously, there's an issue of directionality, like which way do these variables influence each other? For instance, you wouldn't know if this is showing self-esteem and academic achievement. Those are positively related, but you don't know if people who get positive self-esteem are more likely to do well on in classes, or if people who do well in their classes then generate more self-esteem. You don't know which direction it goes, right? And it's also possible that both of those things are true, right? There's a bi-directional relationship such that both of them cause an increase in each other, essentially. But you can't use causal language when you're talking about correlational designs. So what can you say with correlational data? Well, basically, if you see that there's correlations between two variables, it tells you that on average, as one of them increases, some other change in the other one is going to be seen. So a positive correlation is where an increase in one variable is related to an increase in the second variable. You don't say causes, but you can say is associated with or is related to. Versus negative correlation is an increase in one of those variables is related to a decrease in the second variable. And we'll talk more about correlations in a later chapter, but basically you can see there's different sizes and strengths of correlations that can range from -1, which is the most negative correlation, meaning like as something increases, the other variable always decreases, to +1, which is as one variable increases, the other variable always increases, or 0. You could have no correlation, which means that like as one thing changes, if you increase or decrease the first variable, it has nothing to do at all with the second variable. They're not related whatsoever. So like, maybe like weight and GPA or something like that, or height and GPA. Those things should have a very small correlation or 0 correlation. And by small, I don't mean negative. I just mean like those things are not really related at all. And I want to end on a really important note, which is that in psychological science, a single study doesn't prove anything. So we want to avoid using words like prove, like the plague, because the fact is that although we're in science and the business of science is often trying to uncover truths about the world, we can't ever actually really know because we're taking, again, samples from a population and then trying to infer some characteristic of the population from the sample. But we can never be sure if that's the actual sort of capital T truth of the world because it could be that, well, the specific sample we got influences obviously some of the variables and some of the measurements. It could be that elements of the experiment were done poorly and that could affect the outcomes, right? So we never actually prove anything by a single study in science. What we do is over many, many years and having many, many, many iterations of different studies that are all sort of looking at the same constructs and variables, we can start to get a sense for, hey, are other people, and across hundreds of studies, are we all finding kind of the same thing? Then that's going to be pretty good evidence that, yeah, what we're seeing here is sort of how the world works and how these psychological concepts affect each other and how people affect each other and our behaviors and those kinds of things. So we are not going to say prove in this class, but we do definitely want to say things like, well, it suggests, and we have evidence to suggest, and those kinds of things. So anyways, just a note to end on. Thank you very much. All right, let's end on a couple of knowledge check questions. So when we're thinking about variables and conducting research, here's an example. I want to know if consuming fish oil really makes you smarter. So how smart you are, whether or not you consumed fish oil, is an example of which one of these? It's going to be the dependent variable, right? Whether or not I have my sample take fish oil, or part of my sample take fish oil, and another part of it I say don't take fish oil, that would be the independent variable because I'm manipulating that. I'm telling people take fish oil or don't take fish oil. But the outcome, the dependent variable, what we're measuring afterwards, is going to be how smart people in the sample are. All right, how about this one? The average IQ in my sample was 120. This is an example of, that's going to be a statistic, right? So the average in this case is a statistic. And I know that because of the word sample. This is a group of people that I've taken from the population, and therefore data related to them is going to be a group of statistics, whether it's average or whether it's standard deviation or it's some kind of frequency or percentage or something like that. Those are all going to be statistics. If I had said the average IQ in my population was 120, then that would be a parameter. And just for your own information, see here the datum. A datum is a single point of information. So what we would say is if we took one of those participants and asked and performed an IQ exam or IQ test, and their score was 117, 117 would be what we call a raw score. It's just one person's single score, and that would be one datum, which is the singular of data. All right, thanks so much. I'll see you in the next video.